Get very boring very much. Keep changing. So, do you remember? I think 3 weeks back, Raj must have explained you thermodynamic relations just before he started with psychometric properties like humidity, moisture content, relative humidity, specific humidity, all of that. Before that, thermodynamic relations were discussed. You've studied first year or second year thermodynamics, the basic fundamental thermodynamics. I think maybe 2-3 years back, or some of you who have done your diploma 10 years back, maybe 10 years back. Do you know ideal gas law? Everyone knows what's an ideal gas law?
Z equals to 1.
PV equals MRT. Everyone remembers that, right? Now, can you tell me what are the assumptions behind ideal gas law?
Z equals to 1.
Yeah.
Z equals to 1. I do. PV.
Okay, but that's
Compressibility factor.
Of course, yeah.
So what are the assumptions behind ideal gas law? Everyone knows. Can you treat air as ideal gas?
Maybe.
Is it reasonable to assume air as ideal gas? Have you done that before when solving problems in the class? Yes. We could treat air as an ideal gas. Now, PV equals MRT. What are the assumptions behind that? It's a linear equation, right? It's a straight line equation. PV equals MRT. There's no square term. There's no trigonometric term. There's no other logarithmic term. It's a perfect straight line equation. What we say that ideal gases tend to behave very uniformly no matter what. The fundamental assumption behind that, everyone, very important, because in your fourth assessment you have to write those assumptions. Marks will be there for assumptions as well. In your assignment, marks are there for assumptions. For assignment number 3, one of the things in the marking rubric, if you have looked at, is assumption. If you want high distinction, assumptions should be there. All assumptions should be there. And are you dealing with gases in your assignment 3? Yes, exhaust gas is there. And you are going to treat that exhaust gas as an ideal gas. So, one of the assumptions behind ideal gas is particles of ideal gas, molecules, atoms. So let's treat, say, air, all the molecules within the air of oxygen, nitrogen, carbon dioxide, and all the other trace gases. Although they are present, they do not occupy any volume. Can you imagine? Imagine that whiteboard is there, you can see that, right? But doesn't have any volume. Doesn't take any volume. Can you imagine that? Very difficult to imagine, right? That's the idealization. So something is present but doesn't have any volume to it. When we say volume is 0 of anything, it doesn't exist if volume is 0. That's what reality tells us. But one of the assumptions behind ideal gas law, PV equals MRT, is all the particles are present, they do not occupy any volume. The volume they occupy is infinite, like very, 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 very tiny, or almost ignored. Basically, they don't occupy. In addition to that, what else? The second assumption is two particles. Let's say you've got in this air, you've got oxygen molecules, nitrogen molecules, any two molecules. O2, N2, or two O2s, or one O2, one N2. Let's say my fizz is O2 and this is N2. They're next to each other. I'm just trying to help you visualize things, okay? They're next to each other. Like you and me or your classmates, they're next to each other. How do you know someone is sitting next to you? How do you sense my presence? By hearing my voice, by seeing me. There's some kind of sensory action happening between us. That's why you sense my presence, right? I sense your presence. Similarly, in real world, how would an air molecule here would know there's something around it? By intermolecular forces, right? By intermolecular forces. Now, second assumption is in ideal gas law, there is no intermolecular force. They don't exert any intermolecular force on each other. That's an assumption. So even if they're present close together, they don't feel each other. Basically, that's an assumption. only then the so-called ideal gas will behave like an ideal gas. As soon as they start feeling their presence, the intermolecular forces, those forces will start to act and react with each other, and the behavior of that substance will go non-ideal or non-linear. Okay? Makes sense? So, let's try to answer this question. And before we answer this question, can you tell me what are the fundamental properties, which basically the question is telling me the answer, what are the 3 fundamental properties of any matter that can be used to estimate or predict other properties? Try to give me some answer. The wrong answer is okay, as I said yesterday. Just try, it's there. What are the fundamental properties that can be used to estimate or predict other properties of substance? So what are the properties of substances? So let's say that table, what are the properties? Name many properties, right? What are the fundamental properties for that any substance, any matter to exist? It will have some temperature, it will have some volume, it might have some pressure, right? Temperature, pressure, volume, these are 3 fundamental properties. Now, how easy is it to measure temperature of any substance? Can you measure temperature of any substance? If I give you a glass of water, right? So pour water in a glass and give it to you and say, measure the temperature. Tell me what's the temperature of that water. What are you going to do? I'm asking very simple question, very kind of high school or even primary school level questions. But tell me, I'm expecting you to tell me, although the answer is simple, maybe add something extra to it in terms of, don't say just a thermometer. Maybe you're going to use a thermocouple. Have you heard thermocouples? Temperature sensors, or maybe thermistor. So some kind of a temperature sensor, and you can measure temperature. And it's simple to measure temperature, or easy to measure temperature. Now, let's say I give you a gas bottle which is filled with oxygen, nitrogen, and some gas, and ask you how much is the pressure of that gas inside that bottle. How are you going to measure it?
Pressure gauge.
Connect a pressure gauge or some kind of a pressure sensor. Is it easy to measure pressure? Yes. Now, if I say of that gas bottle or the cup of water, how much is the volume of water or the gas? How are you going to measure the volume of gas or water in that container? Just going to measure the geometry, whether it's a circular cylinder, measure the diameter, height, and simple, right? Now, the next question is going to be tricky. If I ask you, with the same glass of water, now you have measured the temperature, I've given you warm water, let's say it's at 50 degrees Celsius, and say, I ask you, how much is the internal energy of that water? What sensor are you going to use? Everyone understand what's internal energy, right? Internal energy is how fast these molecules and particles are vibrating. So how much is the internal energy of that water? How are you going to measure it? Or how are you going to estimate or tell me? What are you going to do? Now this is a practical question, and this is a real world question. As an engineer, you might have to, in your real world as a professional engineer, use this knowledge, and it's very fundamental knowledge. You know that, I'm very sure. But it's not that obvious. Can you measure internal energy of any substance? I mean, as I said, internal energy is vibrations of these molecules. It's very difficult to measure vibration of each molecule or each particle and sum it up. So, okay, if you can't do that, what is another way of estimating? If you can't directly measure internal energy, there's no sensor to measure internal energy because it's an indirect property. It's not fundamental property. Those 3 fundamental properties, temperature, pressure, volume, are easy. Anyone can measure. Now, why do industry needs mechanical engineers like you? What's your job? You know maths behind how to use those 3 properties in combination and mathematically calculate internal energy, for example, enthalpy, entropy, exergy, and then use those to predict how a system is going to perform if it was undergoing some process. That's your role as an engineer. So, can anyone tell me internal energy? Do you remember internal energy? There is an equation, simple equation that we have used. Let's say change in internal energy, U, is proportional to something multiplied by something. Is proportional to something multiplied by something. And equal to, again, we can also call that as is equal to, there will be three terms. So, let me give you some hints. That glass of water originally was at 50 degrees Celsius. The water was at 50 degrees Celsius, okay? And now, I'll give you another glass of water with the same amount of water, same mass, but it is at 60 degrees Celsius. One is at 50, second one is at 60. Which one of them would have more internal energy? Can you tell me that?
60.
Okay, why? Why are you saying that it's 60? What has made you think it's 60, not 50? Temperature. Okay, good. You're coming to that. So, should one of these things be temperature? Okay, so let's look at the first equation. If one of them was temperature, what should be the other one?
Property.
No, not pressure. Not volume, but something related to volume for internal energy. Yes. Now, mass, yeah, mass will go in the bottom one, yes, when it's equal to, for proportionality, there is a proportionality constant, CV. Says specific heat capacity at constant volume. I think you remember this equation. So, CV and T. Here, mass, CV and T. Now, because it's a change, I've added change in internal energy, I need to add change in temperature as well. Make sense? Okay? Okay. So that's a simpler equation. You can use that equation in certain scenarios where you're assuming CV, which is specific heat capacity at constant volume, to be constant property. But in real world, it's not constant, it's a function of temperature. As temperature changes, CV value changes for the same substance. You're not changing its chemical properties. If it's just H2O at 20 degrees Celsius, CV is different as compared to H2O at 50 degrees Celsius, as compared to 100 degrees Celsius. Also, between the phases is different. If it's liquid phase and if it's vapor phase, CV is different. Okay? So, question. That true or false question. Properties such as specific internal energy. Everyone knows what's meant by specific. Specific is per unit mass. So, unit of internal energy will be either joules or kilojoules, whereas specific internal energy, which is, let's say, delta U divided by mass, or delta small u, delta small u, unit is kilojoules per kilogram. Okay, that's the only difference. The reason why we do that, divided by kilogram, to make it independent of mass, and then we can use that property to design and scale up and scale down systems. We can start with a very small volume or mass of the system, and then we can go to a very large. Same calculation, same logic. It's the scaling, for the purpose of scaling. So, properties such as specific internal energy and enthalpy, entropy of a substance are function of pressure, temperature, and specific volume of that substance. Are they functions of those three fundamental properties? True or false? That's true. Okay? So, you might get a question like this in the final exam, like the fourth assessment. Not exactly the same question. I might change it a little bit. You might have a couple of, like, there will be 6 or 7 questions. Some of them might be multiple choice. But you have to think logically a little bit. It's not very difficult, but if exact same question was given, it's a closed book, closed note, how many of you would remember? Yes. If you're paying attention, you would remember. If you're not paying attention for last 7 or 8 minutes I was talking, you won't remember. Okay? So next one. So please pay attention at the next one. It could be this question. Who knows? So everyone knows PV equals MRT, and whiteboard is eraser now.
Yeah.
Oh, they're here. Okay. So everyone knows. That's the ideal gas equation, but you can use this ideal gas equation with a small variation for real gases, and that version looks like PV equals, and let me change that, keep that in there, and P small v equals ZRT, or P capital V equals ZMRT. Okay? So do you know the difference between capital V and small v? What is that small v stands for? Specific volume, which is meter cubes divided by mass. So we are moving that mass there, becomes meter cubes divided by mass, which is that. Okay? Now, what is that Z?
Compressibility factor.
Compressibility factor. Now, what does that tell you? Why do we need to use that Z? It's just because it looks nice and fancy equation? Still it's linear equation. What's that Z?
It's a guess.
Okay, it's one of your classmates saying it's kind of a guess of how the property will vary or deviate from ideal behavior. It's not just a random guess, it's based on some experimental results. So someone has done experiments on real gases, on oxygen, nitrogen, hydrogen, all of these, or air, all of these are real gases, right? We know, we breathe them. And when you move your hand around, you can feel the air, right? So something is there, particles, they are occupying the volume. At the start of this session, I explained to you ideal gas law. First assumption was, particles, they don't occupy any volume. Basically, they are there, but they don't exist. That doesn't make sense. But in theory, things can make sense in theory. Maths can be weird, very weird. And theoretical thermodynamics or theoretical anything can be very strange. So, real gases, they occupy volume. Real gases interact with each other, molecules, and hence they are going to deviate from ideal behavior. Now, how much far away they will deviate is represented, given by Z. So, I hope everyone understands that. That's just a quick revision of things that you have studied in the past. Can you tell me answer for this? For hydrogen, hydrogen being a real gas, right? Compressibility, the compressibility factor Z tends to unity, approaches 1, that value approaches 1 as pressure approaches 0. When the pressure starts going to 0, Z starts going to 1. Is that true or false? Hydrogen being a real gas to begin with. It could, the same, I can change the question and say, for oxygen, exact same, true or false? What do you think? And you have to tell me why it's false. So let's first try to think. What means by Z going to 1? So in that equation, let's forget about all of that stuff. So, okay, let me rewrite that equation in that format. In the same format there, T capital V equals Z M R T. Okay. Now, if I get rid of that Z, that equation is exactly the same, right? So if that z becomes 1, if the value of z becomes 1, replace that by 1. That and that equation are exactly the same. So now is that equation ideal gas equation? Yes. Okay. So when z becomes 1, a gas will behave like an ideal gas. That's the meaning. Or not exactly 1, it might be 0.999999, approaching 1. Okay? It's almost ideal. So now tell me the answer. When will Z tend to unity? Question is saying for hydrogen compressibility factor will tend to unity if pressure is approaching 0. Not exactly 0, it won't be, it will never be 0. We're talking about absolute pressures, okay? We're not talking about gauge pressure. We're talking about absolute. Everyone understands difference between absolute and gauge, right? What's the absolute pressure at the sea level, atmospheric pressure? What's the absolute atmospheric pressure at sea level? Standard. 101.3 kPa or 1 atmosphere. That's the absolute pressure. What's the gauge pressure at sea level?
0.
Just of atmosphere. One of your classmates is saying is 0. If you take a pressure gauge, okay, has everyone seen a pressure gauge, mechanical, like with a needle, yeah, or at least online on screen, if not physically. If you take one of those pressure gauges and just leave it on this bench, will it read anything? What will it read? How much pressure will it read? 0. So if I leave that on the beach at the sea level, will it read anything? So the gauge pressure will be 0, but absolute pressure will be 1 atmosphere, right? So when we say pressure tends towards 0, which we are talking about vacuum, very, very low. I mean, the meaning of that is the pressure is very low. Pressure is very low. So what's going to happen when the pressure is low? Okay, let's visualize. These are two air molecules, or let's say hydrogen molecules. Originally begin with 1 atmosphere pressure. The pressure was 1 atmosphere. There's a vessel and there's hydrogen inside there, and 2 molecules are that far apart, and they're under certain pressure, maybe let's say 1 atmospheric pressure. Now you start reducing the pressure somehow. There's some machine that you turn a switch, and the pressure starts decreasing. Now what's going to happen to the position of those 2 particles? Will they stay at the same place, or will they go away from each other as the pressure decreases? Let's forget about the vessel, because I think you're struggling to visualize the vessel. Let's think about the pressure inside this room. If you want to reduce the pressure in this room, what do you have to do?
Take oxygen.
Take the air out, right? Slowly take the air out. Now, when we start doing that, what happens to the remaining molecules? Are they still cuddling each other and trying to stay together in one corner? Let the rest of the molecules go away. Will they do that? No. What will happen to, let's say, one bunch of molecules which were here? Some of the molecules have been removed from the window. What will happen to them?
Spread out.
Spread out. They're going further from each other. Now, what's going to happen to the intermolecular forces between them? Now, will this molecule still feel the intermolecular force? Will be weaker and weaker and weaker and weaker and weaker and almost nothing. Compared to the entire volume of this room, how much volume will this particle occupy? The remaining particles? Almost nothing. Originally, at present, this room is filled with millions and billions of molecules, right? They do occupy space. But when you start extracting, pressure starts dropping, they tend to occupy almost comparative. We know in the real world, it can never happen that a particle is present and doesn't have any volume. but relative to the surroundings, it's occupying very negligible space. So first assumption was of an ideal gas law, particles occupy almost no space. Second assumption was they don't experience any intermolecular forces. So if you reduce the pressure, will both those assumptions be getting true? So should the Z be tending to unity, and now the real gas might start behaving like ideal? That's true. Clear? So that answer for that is true. Have I confused you guys? I mean, I know I've stretched up the discussion, but it's very important. It's very fundamental discussion, but it's very important for every one of you to realize it. Once that clicks, the more difficult concepts in the future, they get easy. Because a lot of times, my experience with all past students has been, and my own experience as a student like you guys, it was difficult to understand some of the things till the fundamentals were unclear. I mean, once they got clear, everything else was easy. Okay, so yes.
What do you mean by tends to unity?
Tends to means it's going towards 1.
Unity means what?
Yeah, unity means 1. Yes, it tends towards unity, and pressure tends towards 0. So it's not exactly 0. It might be 0.0001, and unity means it's not exactly 1. It's 0.99999. Okay, so we've gone through that. Basically, that's what I was explaining. And there are two different ways in which you could write this equation. You could use basically capital Z, which is absolute factor, compressibility factor. In that case, we are using per unit kilograms mass, not molar mass. In this case, it becomes a molar mass. Now, for real gases, how are we going to predict this value of Z? How are we going to estimate the value of Z? It's impossible really at present, at least mathematically. We cannot mathematically estimate how much is Z. We have to do experiments. We get a new gas, we put in a constant volume chamber. Everyone knows what's a constant volume chamber? CVC, it's industry, it's used, widely is used, constant volume chamber. Just basically a rigid tank. Take a rigid tank like a pressure cooker, put some gas in it and start heating it up. What's going to happen? You start heating it up, temperature starts rising, volume is constant, so volume doesn't change, hence pressure starts rising. So you can measure pressure, temperature and come up with a curve for every temperature rise, like half a degree temperature rise, every half a degree, you measure corresponding pressure and come up with a curve. Say you can change that experiment to a constant pressure experiment, which is a piston cylinder device with almost no friction in there. Minimum friction, or in theory frictionless piston cylinder device. Same gas inside, start heating it up, pressure remains constant, now volume changes. For every half a degree temperature rise, you will get small change in volume. You record that. Use those to estimate, basically compare that with, by keeping volume constant in the first example with rigid tank, like a pressure cooker. How is pressure changing if the temperature rises by so much? You can calculate that using ideal gas, and whatever you have measured, compare them, how much deviation they are, add a correction factor. And that's nothing but a correction factor. Add a factor to bring the ideal behavior to the real behavior. Come up with, so that's how Z values are predicted. Now, usually there will be kind of a polynomial. It's not Z value, Z is not going to be a straight line. So you would have seen these compressibility factor curves. Remember seeing this? Have you ever used these charts, compressibility charts? Never? Maybe in your, as a professional life, you might not have, but in your first thermodynamics, maybe, no? So basically you can read value of Z from these charts. These are academic charts from the book, but industrial charts, you have got more detailed versions of them, and these days everything is online, so you just need to type in specific temperature, specific pressure that you're measuring, and the type of substance or gas you have, and it just in engineering toolbox online it should easily give you value of Z. Now, how to read them? We have to use reduced pressure, and then these are reduced temperatures. Now, what are these reduced pressures and reduced temperatures? Now, think about, let's step back. Don't get overwhelmed with the chart, because I can see most of you have said, no, we have never used this chart. This is the first time you're seeing the chart, most likely, or maybe Raj might have shown it to you and he might have skipped it quickly or gone through, say, you might already know this. Now, do you know what is critical pressure of any substance? No? Do you have property tables? Let me open up one of the property tables. Like water tables, finding HF, HG, VF, VG, VFG, all of those properties of, let's say, water or refrigerant. You see, that's saturated water table. Now, if we look at that column, that first column is temperature, second is pressure. So that's the last temperature and that's the last pressure. What are those values? 373 and 22,064. Those are critical temperature and critical pressures of water. So when you start heating water, your day-to-day experience, everyone makes tea, coffee or something, you have heated water in a pot, I'm very sure, right? And you've physically seen when you heat the water, it starts boiling, and if you keep that water, let it boil, it evaporates and liquid water disappears and there's water vapor somewhere in the air, moisture, right? Now, what happens if you do this process of boiling in a constant volume? So take a vessel like a boiler, a pressure vessel, you add a small amount of liquid water, you start heating it up and it starts boiling, the pressure starts increasing, temperature starts increasing because of heating up, right? And you get some vapor, some liquid. Maybe there might be a point where you might get all vapor, superheated vapor. But then if you continue to heat it up and the pressure continues to increase, if it's a constant volume and the pressure goes very high, and if the pressure reaches 22,064 kPa, which is 22 megapascal, okay? And if the temperature goes beyond that, let's say 400 degrees Celsius. So let's say you've got water at 400 degrees Celsius and let's say 23 megapascal pressure. Pressure is 23 megapascal beyond the critical pressure, temperature is 400 beyond the critical temperature of 373. Tell me, how would that substance, which is still water, H2O, behave? Will it be gas? Will it be liquid? Will it be superheated vapor? Will it be compressed liquid? What will it be? What will be the phase?
Liquefied gas, liquid gas.
It will be critical fluid. It will be gas that behaves like a liquid. Why? Although the particles are far away from each other because it's a gas, but temperature is so high, they're vibrating so fast that they feel like they're very close to each other. So originally liquid particles were there, molecules of water H2O were that close, we heated it up and they're gone, and while they're heating up they're vibrating. Now they're gone critical and they're doing that. So for any given time they still feel the presence of each other and it's like liquid. but it's a gas. So it's critical. So at that point, critical temperature point, so if I drew, let's say, temperature, enthalpy, or volume, or any other diagram. Have you seen this curve before? Saturation curve, yeah or no? That's the saturated liquid line, saturated vapor line, and that point there is the critical point. Okay? So on this side of the curve, everything is liquid. So water that we drink from the tap or bottle will be in this compressed liquid region. Anything on this side is superheated vapor. Anything in the middle is mixture. Now, anything there is critical. It's neither a liquid, neither a gas. We don't know what it is, basically. I mean, we know, but it's very uncertain. Hence, it's a different phase of the fluid. It's a critical phase of it. Now, at that point, we cannot really define whether it's a gas or vapor, so gas or liquid, and hence, we cannot really say which type of equations to use. Whether it's a gas? No, it's not a gas. Is it a liquid? No, it's not a liquid. So, and that pressure is very high. And at that point, let's assume, we could assume, yeah, it's a gas because the temperature is so high. But the molecules are doing that. They're getting very close to each other. So will the first assumption of ideal gas law be valid? Will they sense each other? Or they won't sense each other? What do you think? They will sense each other. So it's not going to be an ideal behavior. Now, going back to the reduced pressure and reduced temperature, those terms there, the way these numbers are calculated for any given gas, let's say reduced pressure, if we are trying to calculate reduced pressure, is the ratio of actual pressure of the gas divided by the critical pressure of that gas. So, P actual divided by P critical. What is meant by P actual? You have got a gas, you have measured the pressure of that gas, that's the actual pressure you're measuring. Now you're getting a ratio of that pressure to critical pressure, and that becomes your reduced pressure. When will that reduced pressure value be? Basically, more or less depend upon the actual pressures. So if the pressure is very high or pressure is low, and in similar fashion, reduced temperature, TR, actual temperature divided by critical temperature. Okay? So, ideal gas also. A real gas tends to behave like an ideal gas when it goes away from critical properties. So, at that point, let's say you've got a gas which is at that critical point. It's not going to behave, we know it's not going to behave like an ideal gas, for sure. Now, when do you think it would start behaving like an ideal gas? Do you know how to draw on a temperature, volume, temperature, enthalpy, volume diagram, how to draw constant pressure lines? Let's say, and that's your critical, and that's your T critical. So definitely here it's not going to behave, this gas will never behave like ideal gas at that point or any other point along this line because it's saturated gas along the line. When would it start behaving like an ideal gas? Which region? This side or that side? Okay, good. On that side. So let's say if the temperature was critical, you have to go further, let's say somewhere there, that's very low pressure. compared to critical pressure. So if the pressure was far away from critical, it will behave like a ideal gas. Another scenario, if the pressure was, let's say, that. If the pressure was that and the temperature was there, would it behave like ideal gas? No, it will be liquid. So if the pressure was low, temperature needs to be very high. So temperature also needs to be maybe critical or close to critical. Close to critical or even above critical, it will behave like ideal gas. So a real gas will behave or tend to behave like an ideal gas if the pressure is very, very low and temperature is high. Those are the conditions. So then we went through van der Waals equation of state. And what is that? That's basically a mathematical version of representing an actual gas, which this equation has been derived from ideal gas equation as well. So if you look at that equation, I'm writing the ideal gas equation. So PV equals MRT, or I move that V there. So P equals MRT over V. That's ideal gas law, right? Everyone is with me? Do you see a similarity between these? Is there a RNT on the right hand side? Yes. Is there a V on the bottom? Yes. That M has disappeared. The reason being we have written small v underneath. So capital V has changed to, we could write this P equals RT over small v. That's still ideal. So it looks like that, but it's not ideal gas. What that represents, what the Waals equation represents, is a real gas behavior. So you can use that for real gases. The only difference in between those two equations are those terms A and B. What is A and what is B? So the question is asking you, the constant B is intended to account for what? And constant A over V square accounts for what? No idea? Guess. Can you guess it? Yeah. Because now I've repeated this few times now. What's the difference between an ideal behavior and the real behavior? What happens to the volume? Ideal particle doesn't occupy any volume. Real has got some finite volume. Molecular interactions, ideal, they don't have any molecular interaction. Real, they do. So those A and B should represent one of those two things. I'm not going to test your memory in the fourth assessment. What I might ask you a question not like that, but I might say, what are A and B's? Just give a general. A and B represent, you can write A and B represent, or they capture finite volume occupied by real gases and intermolecular action between real gases. So answer would be, now take a picture, I think that's better. So constant B is intended to account for the finite volume occupied by molecules. In real gases, yes, they do occupy volume, and A over V square accounts for the forces of attraction between molecules. Is it making sense? Kind of. Don't worry about it. I mean, equation will be given. I will only ask conceptual questions saying, I might just write that equation and say, ask you simple as, is that ideal gas equation? Is it ideal gas equation or is it real gas equation? I might put that question saying, okay, which of the following is this equation for? Ideal gas, van der Waals equation, or magical equation? So you're not going to say that's ideal gas, right? Everyone knows ideal gas is that. So it's not going to be tricky. It will be quite straightforward question when they have multiple choice. Now, although the numerical questions will be a little bit tricky. When I say tricky, in the sense you should be able to practice. So we are going to solve some problems soon. Anyway, at what condition does van der Waals equation of state that the equation written at the top becomes ideal gas equation? Just look at that equation. When would that equation be ideal gas? When the value of A becomes infinity or 0? 0. And value of B becomes infinity or 0? 0. So basically, there's no finite volume. Basically, there's no volume for particles and there's no intermolecular forces. And that will be ideal gas. Okay, so then we went through in my lecture, I don't know whether Raj has gone through this, hopefully he has, two more different equations. So van der Waals and there's Redlich-Kwong, which is kind of an empirical equation, is another version of it, and there are hundreds or even thousands of equations people, engineers like us, have developed over time, because it's still very difficult to predict real gas behavior using mathematical equations. None of these equations will ever predict real gas behavior of all gases. There's no equation right till so far. Humans have not been able to develop any mathematical physics-based equation which can predict how a gas will behave, any gas will behave. They are unique equations. One of the equations might be just for oxygen at a certain temperature and pressure range. There might be another equation for another pressure range, and so on. In case of van der Waals and Redlich-Kwong, you see these values of A and B, they have been tabulated. If you go to your textbooks or data tables, like data books, there will be, for different gases, there will be values of A and B at different temperatures. So you have to read through the table, get the value of A and B, substitute in this equation, only then it will behave, it will predict the exact properties for that particular gas. Real properties. Now, why do we need to study all of this? Why am I explaining all of this where you could simply use ideal gas? Well, that's so simple. Anyone?
Real world applications.
Yeah, like what? That's a very good answer, real world applications. Anyone works in gas industry? No? Anyone works in automotive industry? Auto industry? No? Anyone works in food industry? What kind of industries do you work in? Anyone handles or looks after some gas storage? Do you design pressure vessels, pressure bottles? No? No? Tell me give me an example, anyone who wants to share where you work. I'm very sure you work in mechanical industries, right? Or you work in accounting, all of you. Some of you might, but not all of you. You do some hard kind of in the manufacturing sector, you do some machining, or right? Let's say you're doing some machining or welding. Anyone does welding? No? You might have to use argon gas or some other gas. Let's talk about machining. Do you need to use compressed air for machining? Sometimes, right? There might be pneumatic tools, or there might be just compressed air for cleaning. Okay, let's think about pneumatic tools. Now, if you want to design a pressure vessel that is holding air in it, as a mechanical engineer, you will have to do that. You've selected a compressor, now you want to design size. Design means sizing and how much should be the wall thickness and so on. Now, wall thickness, structurally, integrity of these pressure vessels is something that you're not going to use your own background knowledge to estimate. You're going to use some standards. Okay? So, in Australian standards, in Australia, or whatever the local standards are, they will tell you the exact equation what to use and the procedure. Standards will tell you a procedure. So you just put in the numbers, in steps, and it will tell you, okay, the wall thickness of this vessel should be 2 millimeters or 5 millimeters or whatever that might be. But at the beginning, you have to estimate how much volume of air needs to be stored, and that will depend upon how much is the usage. So you have to estimate, okay, pneumatic tool 1 is using so many cubic meters of air every day. A lathe machine is using so much, an operator is using to clean so much, and so on. And then predict, okay, in a day we need that much air. Now, when we say that much air, you're going to estimate it most likely to begin with in kilograms of air. And kilograms of air doesn't matter whether you're on Earth, Moon, or kilograms is kilograms. Now, volume though is different. So, if you want 1 kilogram of air to be stored under 1 megapascal pressure, at 20 degrees Celsius, how much should be the volume of the tank? Can you estimate that? Now, quick. Pressure 1000, let's say kPa, which is 1 megapascal. Mass 1 kilogram. Okay. Temperature, let's make it let's say 293 kelvins. It should be temperatures in these equations should be in kelvins, always absolute temperatures. R of air 0.287 kilojoules per kilogram Kelvin. Question is, what is the volume? Your responsibility is, someone has given you data and you have estimated you need 1 kilogram of air to be stored, which will be enough for a certain process. Now your job is to figure out how much size of the tank you need. What are you going to do? How are you going to calculate the size? Tell me, what's the size? Are you using this equation? Okay, so let's rewrite that. Make it easy. Yeah, how much is that?
0.084.
0.084 meter cubes, right? So about 0.8 of a liter. Okay, ish. Oh no, sorry, 84 liters. About 84 liters of volume. So can you visualize what's 84 liters of volume? What's 10 liter volume? 10 liter bucket. Have you seen a 10 liter bucket? So can you imagine 8 buckets? So you've estimated that, and you now size it, you design everything, and you say, okay, to your boss, this is what we need to manufacture or get it from some supplier. 84 liters of volume. Your boss relies on you, believes you, and goes and buys 84 liter and starts filling up air, and realize, hang on, either you can't fit 1 kilogram of air inside at that pressure, you need higher pressure, or if you put 1 kilogram, the pressure is not reaching 1 megapascal, it's lower pressure, because you need to add more air in there to get to that pressure. Why? And then your boss starts scratching their head and then approaches you saying, what have you done? What mistake have you made? Why are you giving me a wrong number? And what would be your mistake in that case?
Assuming ideal gas.
Assuming air behaving as an ideal gas. That will be a mistake. Because pressure is quite high, temperature is not very high. So low temperature means molecules are closer together. High pressure means molecules are closer together. They can start feeling each other. It's not ideal behavior, definitely. And you're using ideal gas, not. Rather, you should have used this equation, gone and looked at the table and found what is value for B of air, what is the value of A for air, and then estimated the specific volume from that equation of instead of using ideal gas. And that will be, that's the practical reason why you need to study this. Or you don't need to remember these equations. In real world, I don't remember all the equations. The only reason I'm repeatedly teaching, I might remember some of them, or repeatedly use in research, I might remember some of them, but I know what to, on where to find. I know, okay, if I want to do this, logic approach is there. I cannot be using ideal in the real world. So I will go and find from the book, and that's what, when you're studying, you should study and remember this, that don't make these assumptions in the real world. Back of the envelope, if your boss is asking, give me a quick estimate. You can say, about 84 liters of volume, about 84. And then you would say, but that's not a final answer though. Approximately 84. It might be 80, it might be 70, it might be 95. Who knows? I need to spend half a day to estimate. I mean, and then if your boss is not an engineer, they might say, okay, go ahead, spend half a day and you can Facebook or do whatever you most like. Don't do that. I mean, so, and that's why your job as engineer is very important. Okay. So, then I've gone through in the lecture Maxwell's relations. Why they're important, you don't need to remember all of these, but they help us estimate properties such as internal energy, enthalpy, entropy using temperature, pressure, volume. That's it, these three properties. If you know these three properties, you can find all other properties. Now this example is of, can the enthalpy change associated with phase change, such as enthalpy of vaporization, HFG, be determined using the knowledge of PVT? Yes, it can be. How? Using Clapeyron equation, and that Clapeyron equation comes from Maxwell's equation. And if you look at, I mean, I don't know whether you want to continue your studies in the future, if you want to do master's, PhD, go and explore that, email me in thermodynamics, and I think some of your senior students have started doing PhD. Ask them, or not Raj, Dr. Chandra. He knows. I think a couple of them have got full scholarship, if you're interested. But if you're not interested in research, you don't need to know how to derive these equations in detail, but you need to know some derivation, small amount, and then how to use these equations. So you see, that equation has been derived, it's a Clapeyron equation. Real world application of that will be, let's say you're working for a company like DuPont. Have you heard of DuPont? They make refrigerants. They make different chemicals. Now, property tables, for example, what is HFG? You know, everyone knows what's HFG? In there, that value there is HFG. It's enthalpy of vaporization or condensation. So, if you have liquid, how much amount of thermal energy you need to add to change saturated liquid to saturated vapor? And how much amount of energy you need to extract from vapor to convert it to saturated liquid? That's the value. Now, do you know how these tables were formed? It's not like grows on a tree or something. It's like you guys, engineers, are developing these. Engineers in maybe 1800th century developed these numbers for water. And you would be thinking, wow, how is it relevant to me? There are a lot of other people like chemists, they're developing new fluids every day. They come up with a new fluid and they need someone to estimate the properties of that. And you might be one of the engineers working in the company and a group of chemists, they have developed this fluid. They say, okay, now your job is to estimate, come up with this table. There are machines that you just get a sample, put that sample in the machine does whatever it needs to, and estimate most of the properties. But you need to understand how they work, what the maths behind it. Because if the machine stops working, or the coding goes corrupt or something, you should have a little bit of knowledge to communicate with the technician or do some maintenance on it. And the way these are estimated is using that Clapeyron equation, which is there. Now, that is amount of thermal energy and how we need it to change liquid to vapor or vapor to liquid. What we are using to estimate that? Temperature. Can you easily measure temperature? Yes. Specific volume. Can you easily measure volume and mass? Because specific volume is volume divided by mass. You can measure mass? Yes. How many kilograms of any substance? You can. Can you measure volume? Yes. Now, what about that? That's a relationship between pressure and temperature. Basically, what it's showing is the slope. If we have, let's say, pressure, volume diagram, that slope there, or that slope there. Simple as that. Now, how would you get the curve? Do you know how these curves have been developed? Experimentally, very simple. Again, fundamental two experiments. Constant volume chamber, take a cylinder which is rigid cylinder or tank, put some liquid in it, close it so that the volume is constant, start heating it up, measure temperature, measure pressure. You get a curve, pressure temperature curve. You get a piston cylinder device with almost no friction, exact same, repeat the process, add some liquid, heat it up, measure volume, how much is the piston rising, that gives you the volume change, and how much is the temperature change. That gives you slope for temperature, volume. So dP/dt, constant volume chamber, rigid tank kind of an experiment. You can estimate that. And that has been already estimated for, let's say, for water by someone. So for every change, let's look at those two rows. For change in pressure, how much is the change in temperature? It's known. How has that data been developed? By using, someone has done those experiments, constant volume, heated it up and seen how much pressure is rising for how much temperature change. So you do dP, which is change in the temperature, divided by dt at saturated properties. These are saturated properties. And knowing that, you can then, so change in pressure divided by corresponding change in temperature gives you that slope. Specific volume, how much of the, let's say you start the experiment with few grams, 1 gram of liquid or 1 kilogram of liquid, whatever, and you know the volume of the tank, rigid tank. So volume divided by mass, whatever mass was originally there, gives you specific volume. And temperature is just measured temperature with a sensor. Using these three, you can estimate how much thermal energy is needed or has been absorbed to make that liquid boil or condense. Make sense? I can see you're getting tired, all of it. Too much. Okay. So, similarly, we can do a lot of other things. You can estimate change in entropy, change in internal energy. So you can do change in internal energy, enthalpy, entropy, basically. So what we will do now, and I've shown you how this is derived. We will take a break, maybe, yeah? till 8 o'clock? Because I can see some of you are already falling asleep. So there's no point me continuing. We come back, we can work on the assignment for an hour or so, and then we go back to this, but questions, problems. We solve 2 problems at least. Because I want to make sure everyone is going to get a high distinction in the 4th assessment. Okay? So you have to work with me. We solve 2 problems. That will at least make sure you get distinction or a credit. Okay?
2 questions to get distinction. 2 questions to get distinction.
Now there will be total 6 questions, and these 2 will be the toughest. Why? Because there will be some derivation or some. I can see you're struggling with this. How are you with psychometry, with humidity, moisture, dry bulb temperature, wet bulb temperature problems? Do you remember? Right, solve those problems, right? No? Maybe solve. Tomorrow we'll solve. So there will be 1 problem on psychometry, like a HVAC, heating, cooling. So humidification, definitely 1 question on that. 1 question on one of these, where you have to. I will give you that equation basically, or that equation in the list of formulas. Now what you have to do, I will say for gas X, I'm not going to say for oxygen, nitrogen, I will just make it up. For gas X, CV or CP is a function of temperature. So I will give you an equation, for example. I will say CP equals X plus Y T. That's the equation. Okay? And where X and Y are constants. Or rather than saying X, let's say C1 plus C2 times T. So now I'm going, and the question will say, derive change in enthalpy equation for that gas if Cp is a function like that. So what you have to do there, you substitute C1 plus C2T in there. Everything is okay with integration? Yes? We'll do a little bit of practice. So just integrate that. For first term being a constant, it just disappears. Right? Will it? You're integrating it. Think. Okay. And then in there, I will give you some more information. Equation of state. So I might say that particular gas behaves like PV equals A R T. That's AMRT plus B. Some equation of that gas X. So you have to use that to get that term first. So how would you do a partial differential? Do you remember partial differential? If you want to partially differentiate that, so I'm going to move that m to this side first. So I will move that to there, and that becomes my small v. And what is that partial saying? Partial differential of v with respect to t while keeping pressure constant. Do you remember partial difference? I'm not getting that same response like when I said, do you know integration? No? Okay. There's a short video on, I think this week. I don't know whether you've watched that. It's already there. I've gone through. find that video. I don't know where it's gone. But you can always YouTube it, how to do partial differential. Or what we can do, we'll solve the problem afterwards. When you come back from break, we'll focus on assignment, get you a little bit relaxed with the assignment, and then we'll solve one of the questions. Okay? So that will make you feel confident. That will be one question on deriving an equation. Then there will be one question on heating, like HVAC, which is humidification, dehumidification. Tomorrow we are going to solve similar problem. So today we'll solve this, and you might get one of these, which is the logic will be exactly the same. Once you know how to partially differentiate volume with respect to temperature for constant pressure, you can definitely do pressure with respect to temperature for constant volume. Or if we do that for that, you can do it for this. So it should be, I'm pretty sure you should be comfortable. And then there will be one more question on using gas mixtures. So when two gases are mixed together, let's say oxygen and nitrogen, how much is the partial pressure of that gas? That's another concept that was taught in week 11 or week 10 lectures. So we'll solve problem today. So we'll solve two problems today, hopefully we'll have enough time, and we'll solve two problems tomorrow. That will be more than enough. Okay? And I'm going to share sorry. Yeah, go ahead.
Questions yesterday, they won't be coming out when exams like for economics. Is there any economics question?
Oh, there will be one. Yes, there will be one question on economics. Thanks for reminding that. And it might be a mixed with refrigeration, as I said yesterday, or it might be independent. It might be one of the simple questions. For example, estimate the simple payback, or estimate what is the present value of, let's say, fuel consumed in 15 years. You remember that question? Or in 5 years. I might just reword it a little bit. Instead of 15 years, if I've solved in the class for 15 years, I might say 8 years or 3 years, which is not going to be that different. Logic is still the same. So if you want to estimate the present value of future fuel that you might consume, you remember yesterday what mistake you made? You gave me an answer, that's a good thing, but you made a mistake. And you also made a mistake. You only estimated for 1 year. It should have been 30,000 or something, you estimated 6,000. So don't make that mistake, right? So you have to do year 1, year 2, year 3, year 4, year 5, year 6, whatever the number of years, and sum. These are small things. Equations will be given. So the equations here, I'll put this on canvas. This is the list of formulas that will be provided to you.
Will the slide yesterday and today be shared on the canvas?
I will put those. Yes. Right. Slides that I went through today, I will put them on canvas as well. And this is the list of formulas. I will put them on canvas sometime today or tomorrow morning. And what I want you to do, have a look through them, because tomorrow you're not working, most of you, right? Or maybe half day. In the morning, evening, you can, after our class tomorrow, you can have a look at the list and tell me if you want me to add any more formulas. But you have to tell me by Sunday, because I have to submit this to the admin team for printing. Okay. Okay, go for a break. So come back in maybe 15 minutes.